Hello. In this lesson, we will develop the concept of electric potential. I'm sure you are familiar with the word potential. When we talked about gravitational potential energy in Physics 1, you know that when an object is raised, if I want to raise an object, I need to do work. Is that right? I need to do work. The work done to raise an object in a gravitational field gives it potential energy. That means the amount of work I did is a measure of the positive potential energy of the object. How about the amount of work gravity did? You see, the force I am applying is in the direction of motion. So the work I did is positive. But the force of gravity is downward. That means the displacement of this object is opposite to the direction of the gravitational force. That means the work done by gravity is negative. So the potential energy of this object, I can define it as a measure of the work I did, or it is negative of the work done by gravity. They are basically the same thing. The work I did is a positive quantity. The work gravity did is a negative quantity. Well, let's try and understand that a little more detail. Now, we will compare gravitational and electric fields. How do you compare gravitational and electric field? There are very many common things about a gravitational field and an electric field. You are familiar with gravitational potential energy. We just talked about here. Now, an external force does work against gravity to raise an object. That means the work done by the external force gives this object a certain amount of potential energy. So we can say the potential energy of this object is a measure of the work done by the external force. At the same time, gravity is pulling it down. So gravity does an amount of work, which is the same as the amount of work I did, but opposite. The work done by gravity is negative. Now, work done by gravity always wants to pull objects towards the surface of the earth. Now, where is the potential energy a minimum? The potential energy is a minimum at the surface of the earth. That means the tendency of a gravitational field is to make objects move towards a low potential. A very simple idea. So gravitational field always make things move from a high potential to a low potential. The work done by gravity on the object is negative. There you are. Gravity does negative work. Now, this work done by the external force, the work done by the external force is a measure of the potential energy of the object. Now, potential energy is a measure of, therefore, the negative work done by gravity. Is that right? Work done by the external force is the same as the negative work done by gravity. So, we are going to define gravitational potential energy as the negative of the work done by gravity. Now, when the object is allowed to fall, what will happen? When the object is allowed to fall, gravity will do positive work on it. The object will fall in the direction of the force. So, when the object is allowed to fall, the gravity does positive work. Now tell me, therefore, what is the total work done by gravity on this object when I move this from the surface of the earth to a height and then drop it? what is the net work done by gravity? While raising it, the work done by gravity is negative. While allowing it to fall, work done by gravity is positive. The net work done on the object in a closed path, therefore, is zero. In a gravitational field, the net work done by the force of gravity, I'm not talking about work done by me or anybody else, work done by the force of gravity on an object in a closed path. That is, you raise it up and then leave it, the object moves in a closed path. And that work done in a closed path is zero. Now, a force field, you need to understand this statement. A force field where the net work done is zero in a closed path. A force field where the net work done in a closed path is zero is called a conservative field. Gravitational field is a conservative field. Why? Because the net work done on an object, when the object is raised, gravity does negative work. When the object is dropped, gravity does negative work. The total work done in that closed path by gravity is zero. Therefore, gravitational field is a conservative field. Now, potential energy in a conservative field, therefore, will be defined as, do you remember how we define gravitational potential energy? The gravitational potential energy is negative of the work done by gravity. If U is the potential energy, it's a measure of the negative of the work done by gravity. So, potential energy in a conservative field is negative of the work done by that force, or F ds. F is the force, ds is the small distance moved, and therefore force times distance is the work done. The potential energy is a measure of the negative work done by a conservative force field. That idea must be very clear to you. Well, like gravitational field, electric field is a conservative force field. Can you visualize that? Well, suppose there is an electric field going from left to right. In order to move a positive charge from right to left, I have to do work. That means the electric field is doing negative work. And if I leave that charge is going to fall. When I say fall, it's going to move in the direction of the electric field, just like an object in the gravitational field falls. So, just like gravitational field, an electric field is a conservative force field. Here, we study the motion of electric charges in an electric field. So, the study of electric charges in an electric field is analogous to the study of motion of objects in a gravitational field. Okay, since there are two types of electric charges, now this is where the difference lies. In the case of gravitational field, all objects, you see, falling objects all have masses. So it's a mass that is falling, it's a mass that is moving in a gravitational field. There is no difference there. But when it comes to electric field, we have two types of electric charges. So in order to make our study standardized, we need a test charge. Now, we talked about this before. What is our test charge? Our test charge is a unit positive charge. So, we will not consider negative charge as a test charge. So, when we talked about electric field as a conservative force field, we will be looking at how a positive charge behaves. So our test charge, since there are two types of electric charges, we will take the positive charge as the standard test charge. Alright. Now here I have the electric field caused by a positive charge. That means the electric field is directed to the right. Now, a positive test charge, look at the positive test charge placed at A. A positive test charge placed in the field produces a... Now we have a positive test charge placed in the electric field caused by a positive charge. So that means we have this test charge placed in the field that goes from left to right. Okay. An external force has to do work to move this test charge from A to B. Is that right? If a positive test charge is to be moved against the electric field, an external force needs to do work. Just like an external force needs to do work in raising an object. So, now the electric field does therefore negative work. If an external force does positive work, from moving it from A to B, that means the electric field does negative work. Same way as the gravitational field. So the electric field does negative work on the test charge, increasing its potential energy. You see, whenever work is done on an object to move it, its potential energy increases. So if you move the test charge from A to B, its potential energy increases. And what is the measure of that potential energy? The potential energy increase. The increase in potential energy is a measure of the negative of the work done by the electric field, not the work done by the external force. It's a positive measure of the work done by the external force, but it's a negative measure of the work done by the electric field. Is that right? Because the electric field is a conservative field. When the test charge is allowed to move, once you place the test charge at B, if you allow it to move, it will fall back to A. It will move in the direction of the electric field. It falls. I want you to understand the meaning of the word fall, because most of us are conditioned to believe that falling means this. Well, in this context, falling is moving in the direction. You see, from A, an external force was used to move it from A to B. If you now leave it, the test charge will fall back to A. So, it falls to low potential. Now here, I'm going to use the word potential just like in the gravitational field. So, which of these 2 points is at a higher potential, A or B? When the charge is moved from A to B, its potential increases. So B is at a higher potential. The positive charge moves from a high potential to a low potential. That's something that you need to really know. The direction of motion of a positive charge is from a high potential to a low potential. Just like the direction of motion of an object is from a high potential to a low potential. Our positive is our test charge. Therefore, the direction of motion of a positive charge is from a high potential to a low potential. That means, what will be the direction of motion of a negative charge? From a low potential to a high potential. Alright, we will talk about that as we move on. But at the moment, our standard test charge is a positive charge. Alright, so the potential decreases in the direction of the field. This is the direction of the field from left to right. And as you go away from the charge, the potential decreases. So you must understand the electric potential near a positive charge is a high potential, and the electric potential near a negative charge will be a low potential. An electric charge will move from a high potential to low potential. That means, another important information, the direction of an electric field is the direction of decreasing potential. In the same way, the direction of a gravitational field, you see, gravitational field is directed downward. What is the direction of the gravitational field? The direction of decreasing potential. In the same way, the direction of an electric field is the direction of decreasing potential. The potential decreases in the direction of the electric field. Now, the potential energy of the test charge at infinity is 0. That's what we're going to consider. You see, the potential energy increases as we move the test charge closer and closer to the positive charge. As you allow this test charge to move away, it will move all the way to infinity where the potential is 0. So the potential energy of the test charge at infinity is 0. When the test charge is moved opposite to the direction of the field, if you move the test charge opposite to the direction of the field, what happens? The potential, it gains potential energy, or the gain in potential energy is a measure of the negative work done by the electric field, just like we talked about in the gravitational field. So when the test charge is moved opposite to the direction of the electric field, the gain in potential energy is a measure of the negative work done by the force field. Or we write the same equation we wrote for the gravitational field. The increase in potential energy U is negative of the work done by the electric field. Alright? So these concepts need to be clear in your mind when we talk about electric potential. Alright, consider an electric field E generated by a positive charge. Now here I have a positive charge and an electric field is generated around it. Alright, so that's the electric field E. Since E varies with the distance from the charge, is that right? If you move away from the charge, the intensity of the electric field decreases. Now, what is the expression, what is the equation for intensity of electric field at a point? The strength of the electric field at a point, distance r from a charge. Anybody recall that? Electric field E equal to kq over r squared, where r is the distance. So as the distance changes, the electric field also will change. A test charge Q0 placed in the field experiences the force F equal to EQ0. Is that right? Because electric field is the force per unit charge. The force experienced by a charge Q0 placed in the field E is F equal to EQ0. So if I place a test charge Q0 there, oh well, the Q0 will experience the force given by F equal to EQ0. Well, this is where I have placed the test charge. Well, it went over there without my permission. Okay. To move the test charge in the direction of the increasing potential. What is the direction of increasing potential? If the test charge is here, the direction of the increasing potential is like that. To move the test charge in the direction of the increasing potential, we will need to do an amount of work. The external force, an equal and opposite external force is needed. If this is the force experienced by the electric charge when placed there. In order to move it in the opposite direction, an external force needs to do work on it. And that is given by F equal to negative EQ0. That will be the work done by the external force to move it in the opposite direction. There you are. That is F equal to negative EQ0. The work done by an external force to move it in the direction of increasing potential. Alright? Now, when the test charge is moved a distance dr opposite to the direction of the field. Now, if this is the applied force, and if you move that test charge a little distance dr, what is the work done? If this is the displacement dr, what is the work done? Work done is a measure of the increase in potential energy. The increase in potential energy is therefore negative EQ0, that's the force, multiplied by the distance. Force multiplied by the distance is a measure of the work done, and that is a measure of the increase in potential energy. Now, the increase in potential energy per unit charge. Now, this is the increase in potential energy of a test charge Q0. Therefore, can you tell me, what is the increase in potential energy per unit charge? All we need to do is divide both sides by Q0. We get du over Q0, that is potential energy, increase in potential energy per unit charge, equal to negative EdR. A very interesting equation. The increase in potential energy per unit charge equal to negative EdR, where E is the electric field and ER is the small distance moved. Now, this is a measure of the potential difference between the 2 points. You see, this is the distance dr. Originally, the test charge is here, and now it's been moved and kept here. This quantity, du divided by Q0, in other words, it is potential energy per unit charge. Now, if I want, I can also say work done per unit charge. Is that right? Because potential energy is a measure of the work done. So, potential energy per unit charge is also a measure of work done per unit charge. Now, what do you call that? This work done per unit charge is called the potential difference between the 2 points. A very important concept. What is the definition of potential difference between 2 points? I will ask you a couple of days from now again this question. What is the definition of potential difference? Potential difference is a measure of the work done per unit charge to move it from one point to the other. That gives you a measure of the potential difference between 2 points. So, if this is position A and this is position B, the work done to move it from position A to position B per unit charge, work done per unit charge, is a measure of the potential difference between the 2 points. Alright? So we say, this is something we already know. Potential difference, the work done per unit charge, this is a measure of the potential difference. So we will say potential difference equal to negative EdR. Now we will use uppercase V to represent potential at a point and delta V to represent potential difference between 2 points. So from now on, we will use V for electric potential and delta V for potential difference between 2 points separated by a small distance dr. In such a case, du divided by q0, in other words, potential energy per unit charge, which is the same as work done per unit charge, du over q0, which is called the potential difference between the 2 points, equal to negative E delta R. So, therefore, look at the way I'm going to solve for E. Therefore, E equal to negative delta V divided by, I'll replace the dr by delta R. dr and delta R simply means a small distance. So, electric field is the negative of change in potential divided by the small distance. Okay? A very important equation. Okay, now what I'm going to do is I'm going to start from here now let us consider 2 points A and B in the electric field produced by this charge Q. Now this is Q. I think my Q got very much close to that red line, so please read this as Q. We got 2 points A and B in the electric field produced by the charge Q. Now tell me, which is at a higher potential? Is A or B at a higher potential? Well, B being farther away, B is at a lower potential. The direction of an electric field is the direction of decreasing potential. So A is at a distance R1, so this is the distance R1, and B is at a distance R2 from the charge. Alright, it can be shown that the electric potential V1 at A, here again I am not deriving the equation for you, I am going to give you the equation. So I can show, or we can show by proper mathematics, that the potential V1 at A, distance R1 from the charge Q, is V1 equal to KQ over R1. Now, please do not confuse between electric field at a point and electric potential at a point. Electric field at a point distance R is KQ over R squared. It is a vector quantity. It has a direction. Whereas electric potential at a point distance R1 from a charge is KQ over R1. Electric potential, is that a vector quantity? No, it's a scalar quantity. Alright, similarly the electric potential V2 at B. Can you write the expression for the potential at B? V2 equal to KQ over R2. Therefore, the potential at a distance R from the charge Q, if you want to write a general equation, what will be that equation? The potential at a distance R from a charge Q is given by V sub R. In other words, potential at a distance R equal to KQ over R. And that is the equation for the electric potential. Now, once again, I'm going to warn you, do not confuse between electric field at a point due to a charge and electric potential at the same point. Alright, now here I have, consider the electric field between a positive charge and a negative charge. You are familiar with this. We have talked about this. We have drawn and constructed this electric field. Field lines start from a positive and end in the negative. So we have the electric field between a positive charge and a negative charge. The potential at a distance R from the positive charge is V equal to KQ over R. So if you have the positive charge, we would say the potential at a distance r from it is kq divided by r. Now, the potential near a positive charge is a positive potential. In the same way, the potential near a negative charge is a negative potential. The potential at a distance r from the negative charge is V equal to negative kq over r. So, you can see potential at this point due to this negative charge is a negative value. Not because it is a vector, but because the potential due to a negative charge is a negative value. The potential due to a positive charge is a positive value. Now, that means, tell me, what is the electric potential midway between this equal negative and positive charge? If the potential at this point due to the positive charge is a positive potential, the potential at that point due to the negative will be a negative potential, and they will cancel each other. Now, potential at a point in an electric field. Now, here's the definition of potential at a point in an electric field. We actually worked up that definition as I was taking you through these various steps. What is the definition of potential at a point in an electric field? We said earlier that potential energy per unit charge or work done per unit charge is a measure of the potential at a point. So the definition of potential at a point in an electric field is it is a measure of the work done in moving a unit test charge from infinity to that point. So if you want to define electric potential at a point, electric potential at a point is a measure of the work done in moving a unit charge all the way from infinity to that point. Why infinity? Infinity is the place where the potential is zero. Is that right? So the amount of work done per unit charge to move a unit charge from a place where the potential is zero to the given place is a measure of the potential at that point. So, since potential is the work done per unit charge, what will be the unit for measuring electric potential? Electric potential is a measure of the work done per unit charge. It is joules per coulomb. Electric potential is measured in joules per coulomb, and we call it the volt. A joule per coulomb is called the volt. So electric potential is measured in joules per coulomb, called the volt, and we will use the uppercase V to represent that. V, volt, equal to joule per coulomb. Now, you remember this, don't you? Electric field is negative of delta V divided by delta R. What does that mean? Well, let me show that to you. Give me a second. Well, what that means is if you got 2 points separated by distance delta R, and if the potential difference is delta V, it means the electric field. You see, we will assume that the electric field is uniform in that region. If the electric field is uniform in that region, that electric field will be equal to negative delta V over delta R. In other words, the potential difference divided by the distance between the 2 points will be a measure of the electric field. And therefore, we also have delta V, therefore, is negative E times delta R. All these are important relations, will come very handy when you want to solve problems. Okay. Now, let me ask you, is Newton per Coulomb the same as volt per meter? How can you say Newton per Coulomb is the same as volt per meter? Volt per meter. Well, let's take a look at it. Now, a Newton, what is a Newton? Anybody tell me what a Newton is? A Newton is kilogram meter per second square. Now, per Coulomb, it will be this. Kilogram meter per second squared divided by Coulomb. Now, what is a volt? We said a volt is joules per Coulomb. A volt is joules divided by Coulomb. So a volt per meter is joule divided by Coulomb times meter. Now, what is a joule? A joule is work done per second. Is that right? Work done per second. That is, work is, a joule is a Newton second. So that is Newton second divided by Coulomb meter. Now, what is a Newton? You tell me what is a Newton is. A Newton is kilogram meter per second square. Is that right? Kilogram meter per second square. And you can see that is the same. Kilogram meter per second squared divided by Coulomb. And therefore, Newton per Coulomb is the same as volt per meter. I want you to work this out on your own one more time, because you must be familiar with converting unit from one form to another. Alright, let's do an example. An infinite plane surface charge of surface charge density plus 2.5 microcoulomb per meter squared is in the YZ plane. Well, that's familiar to you. What is the magnitude of the electric field in Newton per Coulomb and in volt per meter? Now, is Newton per Coulomb different from volt per meter? We just showed that they are the same. Now, what is the direction of the electric field for positive values of x? Okay, you need to picture this problem. Now, here is the plane charge that has a charge density sigma equal to positive 2.5 microcoulomb per meter squared. So if this is carrying a positive charge, the electric field will be like this, will be directed towards the x-axis. Alright, the electric field due to an infinite plane charge of density sigma. We did this. Anybody remembers the expression? What is the electric field at a point due to a charge on an infinite plane charge? The electric field due to an infinite plane charge of surface charge density sigma is, we obtained that equation about 2 classes ago. E equal to sigma divided by 2 epsilon naught. That means the value of this electric field anywhere here. You see, it will not be different when you move from place to place. Why? Because this is an infinite plane charge. So the electric field is sigma over 2 epsilon naught. Sigma is given to us. Epsilon naught, we know, we always carry it with us. And that will be 1.41 times 10 to the 5 Newton per Coulomb. Now, the field is directed to the right in the positive x-axis. Now, this is Newton per Coulomb. Is it the same expressed in volts per meter? Yes, we just showed that Newton per Coulomb and volts per meter are the same thing. Alright, the second part of the problem. what is the potential difference VB minus VA when the point B is at a distance x equal to 20 meter and point A is at x equal to 50 meter? What is the value of VB minus VA? If you remember, we had an equation there. We have delta V, the potential difference, equal to negative E delta R. We know the value of E, which is a uniform electric field. We know delta R. Delta R is 50 minus 20, that is 30. Is that right? So once you know that equation, the problem becomes simple. We have delta V equal to negative E dr. Therefore, VB minus VA is negative E times, because VB, B is the first point, the distance dr will be then x1 minus x2. So VB minus VA equal to negative E x1 minus x2. That's x1, 20, and that is x2, that is 50. And that is negative, what's our E? We calculated our E. E is 1.41 times 10 to the 5, that's the one we calculated in the last slide, times 0.2 minus 0.5, and that is the measure of the potential difference. That is 4.23 times 10 to the 4 volt. Okay, I'm going to ask you a question now. Alright, think about this and try and answer this as best as you can. The potential difference between points B and A is this. Tell me which is at a higher potential. Alright, B. A is at a lower potential. That means in order to move a positive charge from A to B, you need to do work. Alright, give me an explanation of this. What does this mean to you? When we say the potential difference between A and B is 4.23 times 10 to the 4 volt, what does it mean to you? Remember, potential difference or potential is a measure of the work done per unit charge. So, this is the potential difference between A and B, means in order to move a unit charge is 1 coulomb. In order to move 1 coulomb of charge from A to B, we've got to do an amount of work 4.23 times 10 to the 4. You see, volt means joules per coulomb, work done per unit charge. That is the meaning. You must understand that. Alright, VA minus VB is a measure of the work done per unit charge that is moved from A to B. Now, we've got a C part. What is the work done to move 1.5 nanocoulomb from A to B? Well, what did we say this quantity is? This quantity is a measure of the work done to move 1 coulomb of charge from A to B. Therefore, what is the work done if you want to now move 1.5 nanocoulomb from A to B? It will be work done per unit charge multiplied by the amount of charge. So the total work done is the work done, the amount of charge, which is 1.9 times, 1.5 times 10 to the negative 9 coulomb, times the potential difference, which is the work done per unit charge, and that will be 6.35 times 10 to the 4 joules. That is the amount of work. No, that is not correct. It's not right. It must be 6.35 times 10 to the negative 4. Put that in your calculator and correct that value. I have always warned you, there are obvious printing errors, spelling errors, and small errors like this. You must not simply leave them. You must be an active learner following every step that I'm going through, so that if you find a small error like this, correct it, email me and tell me about these errors. I would like to hear from you so that I know you are keenly following these. Okay, let's do another problem. A positive charge of magnitude 2 microcoulomb is at the origin. What is the electric potential V at a point 4 meter from the origin relative to V equal to 0 at infinity? How much work must be done by an outside agent to bring a 3 microcoulomb charge from infinity to R equal to 4 meter? Assuming that the 2 microcoulomb charge is held fixed at the origin. Alright, what do we have? A positive charge of 2 microcoulomb is at the origin. There you have. What is the electric potential V at a point 4 meter from here? What is the electric potential here? What's the equation for electric potential? Electric potential at a point distance r from a charge is kq over r. So VR, potential at a distance r, is kq over r. We know our k. Q is 2 microcoulomb and the distance is 4 meter, and that is 4.5 times 10 to the 4 volt. Well, that is the potential at that point. What does that mean? It means in order to bring 1 coulomb of charge from infinity to place it at that point, you need to do that much work. That's the meaning there. B part. How much work must be done by an outside agent to bring 3 microcoulomb charge from infinity to R equal to 4 meter? You see, once you understand what potential at a point means, potential at a point is a measure of the work done per unit charge to do what? Bring that unit charge from infinity to that point. So in order to bring 1 coulomb of charge from infinity to this point, the amount of work done is this 4.5 times 10 to the 4 joules per coulomb. And therefore, if you want to bring how much? 3 microcoulomb charge from infinity to here, how much is the work done? It is work done per unit charge multiplied by the amount of charge. Alright, so work done to move 3 microcoulomb is the 3 microcoulomb multiplied by work done per coulomb, which is this, and that will be 0.014 joules. Okay, what's the next part? C. How much work must be done by an outside agent to bring the 2 microcoulomb charge? Suppose this 2 microcoulomb is not there to begin with, but the 3 microcoulomb is there. Then how much work needs to be done to bring that 2 microcoulomb from infinity to that point? That's the question. Now we have a 2 microcoulomb at x equal to 4. There you have a 2 microcoulomb, and the original 2 microcoulomb is not there anymore. Alright? Now, potential at the origin due to the 3 microcoulomb at x equal to 4, well, this is not the 2. This is the original 3 microcoulomb that is sitting there. Alright? So correct that. This is the original 3 microcoulomb that is sitting there. Now, what is the potential at the origin due to that 3 microcoulomb? V equal to kq over r. Q is 3 microcoulomb divided by 4, and that is 6,750 volt. Now, 6,750 volt is the potential at the origin due to this 3 microcoulomb. That means the amount of work that needs to be done on 1 coulomb to bring it from infinity to the origin is 6,750 volt. And therefore, how much work needs to be done to bring this 2 microcoulomb from infinity? So this is the work that needs to be done to bring 1 coulomb from infinity to the origin. Therefore, work that needs to be done to bring 2 microcoulomb from infinity to the origin is this multiplied by 2 microcoulomb. So that will be 2 microcoulomb multiplied by 6,750 joules per coulomb. That is 0.014 joules. All right. They are beautiful problems. Okay, let's do another problem. 3 point charges are on the x-axis, Q1 at the origin, Q2 at x equal to 3 meter, and Q3 equal to x equal to 6 meter. Find the potential at the point x equal to 0, y equal to 3. If Q1 equal to Q2 equal to Q3 equal to 2 microcoulomb, and B, Q1 equal to Q2 equal to 2 microcoulomb, and Q3 equal to negative 2 microcoulomb. Now read that problem one more time and see whether you can place what this is. Can you picture it? Well, this is what it is. 3 point charges are on the x-axis, Q1 equal to Q1 at the origin, Q2 at x equal to 3, Q3 at x equal to 6 meter, and in the first case we have Q1 equal to Q2 equal to Q3, all of them are 2 microcoulomb. We need to find the electric potential at x equal to 0, y equal to 3. Here, this is the point where I want to find the potential. That means, to start with, you need to find the distance of this point from each charge. Can you find the distance of each? This distance is of course 3. So R1 equal to 3. What's R2? This is the diagonal of this right triangle. So R2 is square root of 3 squared plus 3 squared. So if R1, R2, R3 are the distances of Q1, Q2 and Q3 respectively from the point 0, 3, then we have R1 equal to 3 meter, R2 equal to square root of 3 squared plus 3 squared, that is square root of 18 meter, and R3 equal to square root of 6 squared plus 3 squared, that is square root of 45 meter. Alright, we have Q1 equal to Q2 equal to Q3 equal to 2 microcoulomb. What is the potential at P due to Q1? Well, if you know the potential equation, potential at a point due to a charge is KQ over R. So that will be KQ1 over R1. Now put all those values. Q1 is 2 microcoulomb and R1 is 3, and that will be 6,000 volts. That's the potential at P due to Q1. What is the potential at P due to Q2? It will be KQ2 divided by R2, and put those values. KQ2 divided by R2 is square root 18. That is 4,243 volts. What is the potential at P due to Q3? It will be KQ3 divided by R3, and we know all those values. So just plug in those values. K times Q3 is 2 microcoulomb, R3 is square root 45, and that is 2,683 volts. Therefore, what is the total potential at this point? All the potentials are positive. all these charges are positive, therefore the potential at P due to each of these is positive. That means they will all simply add up to give you the total potential. The total potential at P is 6000 volts plus 4243 volts plus 2683 volts. That is 12,926 volts is the total potential at P. Alright, give me one sentence in your own language. What does that mean to you? What is the meaning that potential at P is this many volts? Can you tell me that? Well, it means in order to bring one coulomb of charge from infinity, where the potential is 0, to this point is these many joules. A volt is joules per coulomb. Now, you notice that there is a B part. Let me go back to that. I have a B part in here. I'm going to leave that for you to do. Well, when you do this, you understand that the potential due to Q1 and Q2 will be positive, and the potential due to Q3 will be negative, and therefore the total potential will be the potential due to the first plus the second minus the third. Now, alright, try that on your own and let me know. Alright, let's do another one. A sphere with a radius 60 centimeter has its center at the origin. Equal charges of 3 microcoulomb are placed at 60 degrees intervals along the equator of the sphere. What is the electric potential at the origin? What is the electric potential at the North Pole? Now, you know that I have a sphere handy here. I keep my basketball. I used to be a basketball player in my old, many years ago. Well, here you have a sphere with the radius of 60 centimeter and its center at the origin. The center of the sphere is at the origin. Equal charges of 3 microcoulomb are placed at 60 degrees interval along the equator. Now look, this is the equator. Is that right? So place the charges at 60 degrees interval. So how many charges can be there? There's one there, 60 degrees the second charge, another 60 degrees the third charge, another 60 degrees the fourth charge, and so on. So it'll be how many? 6, is that right? 6 times 60 is 36, 360 degrees. Alright, let me see if I can draw a diagram of that. The diagram, well, this is the best I can do. What I have done is, I have taken a cross section. So this circle you see is, that circle you see is, if I cut this sphere into half, the cross section circle is what you see. And this is the pole. Alright? Okay. And the charges Q1, Q2, Q3 up to Q6 are all 60 degrees apart. Now what do we want to find? What is the electric potential at the origin? The origin is the center. That means the distance of each of these charges from the origin is the same. What is the distance? What is the distance of each of these charges from the origin? Equal to the radius of the sphere. What's the radius? Are we given the radius? 60 centimeter. That means the distance of each of these charges from the origin is 60 centimeter. We know the charges, we know the distance of the charges from the origin, therefore we can find the electric potential. Is that right? And it's very simple because each of these charges are the same, and the potential due to one is kq over r, where r is the radius here, and therefore potential due to 6 of them will be 6 kq over r. Is that right? Very simple. So we got all the charges equal, the distances of all charges are the same. equal to 0.6 meter. The potential due to each of these charges at the origin is the same, namely kq over r. Therefore, the total potential due to all the 6 charges will be 6 kq over r. And that will be, we know K, we know Q is 3 microcoulomb, divided by R is 0.6. And that is 2.7 times 10 to the 5 volt is the potential at the origin. Well, now we need to find the potential at the North Pole. Now, if you notice, before we go to the next slide, let's talk about it. If this is the North Pole, notice that this line, well, I had cut the sphere into half. So this line is from the center to the North Pole. It's a vertical line like that. And this is therefore the hypotenuse of the right triangle formed by, what's this? This is one leg, this is the other leg. And each of these is the radius, is that right? This is the radius 0.6. This is the radius 0.6. Therefore, what is that distance, the hypotenuse? It is square root of 0.6 squared plus 0.6 squared. And that is the distance of the pole from each of the charges. Once you understand that, the problem becomes easier. Again, all the charges are the same. The distance of the North Pole from each of the charges is the same, namely that distance, which is the hypotenuse of this right triangle. And that will be square root of 0.6 squared plus 0.6 squared, and that is 0.85 meter. And so, the potential at the pole now will be 6 kq over r, where r is now 0.85 meter, alright, and that's equal to 1.9 times 10 to the 5 volt. Okay, what you need to do is, after watching this, you must work out these on your own, and then only you will be able to do a problem on your own. Potential inside and outside a spherical charged shell. Now, do you remember, in connection with Gauss's law, we talked about the electric field inside a spherical shell. We said if you have a spherical shell, the electric field inside is 0. If the electric field inside is 0, what is the electric potential inside? Well, if you do a little calculus, it would have been easier. But if you remember, electric potential or electric field is actually the rate of change of potential. We said delta V divided by delta R. Isn't that what we call the rate? Now, if the rate of change of potential, which is the electric field, is 0. Now, does your mathematical understanding allow you to understand that the rate of change is 0 happens only for a constant number? Suppose you have been working for 10 years, and all these 10 years you have been paid $10 an hour. What is the rate of change of your pay? Well, 0. Is that right? You haven't been given a raise. So, if your pay is a constant, then your rate of change is 0. So, if inside of a charged shell, if the electric field is 0, electric field is the rate of change of potential. That means the potential has to remain a constant. Well, consider a spherical shell of radius r carrying a charge q. In order to find the potential at any point outside the shell, the charge on the shell can be considered to be a point charge concentrated at the center. The potential at a distance r from the center of the shell can then be written as VR equal to KQ over R for any distance greater than the radius. That means if you have a shell which carries a charge Q, the potential at any point outside that shell will be KQ over R, where R is the distance of that point from the center of the shell. Now, this is true only for any point outside the shell. Now tell me, what is the electric potential inside the shell? We just talked about it. The only way electric field can be zero is that the potential is a constant. Now tell me, what is the electric potential on the surface of the charged shell? It will be KQ over R, where R is that radius. The potential on the surface of the spherical shell will be KQ over the radius. And if the potential inside has to be a constant, that means everywhere inside the shell, the potential has to be KQ divided by the radius. And that is the way it is. Alright. Thus the potential on the surface of the shell, V surface, is KQ divided by R. This is the potential on the surface, KQ divided by R, where R is the radius. Now, so V surface is KQ divided by R, and potential anywhere outside the surface is KQ divided by small r, where that r is the distance there. And inside the shell, the electric field is zero. The electric field is zero means the potential must be a constant. That means anywhere inside the shell, the potential has to be the same as the potential on the surface. Then only it can be a constant right through. Since the potential on the surface is V surface is KQ over R, the potential at any point inside the shell also must be the same value. So if you want to summarize all that, how will you say all these things together? You have a charge Q on a shell. The potential at any point outside the shell will be KQ divided by R, where R is that distance from the center. The potential at any point on the surface of the shell will be KQ divided by the radius of the shell. And finally, since the potential at any point inside is a constant, that constant value will also be KQ divided by R. What is an equipotential surface? The name itself suggests equipotential surface, a surface where the potential is the same all over. A surface where the potential is the same all over is called an equipotential surface. Now, the electric field on the surface of a conductor. Now remember, we talked about it. If you have a conductor, the electric field at any point on that conductor has to be at right angles. We discussed that in the last class. If there is a component of the field along the surface, that field will make the electric charges to move. And since it doesn't happen, there is no electric field along the surface. Means electric field is at right angles to a conductor. That means there is no electric field on the surface of a charged conductor. Let me bring back my basketball again. If there is no electric field on the surface of this charged conductor, what can you say about the potential on the surface of the conductor? Well, no matter what the shape of a conductor is, the potential will be all the same all over. Why? Because the electric field on the surface of the conductor is zero, the potential has to be a constant. Alright? Now, you can see the electric field is at right angles. You can see I have shown here the electric field cannot have a component along the surface. Why? If there is a component, it will make electric charges move in the conductor. Since it doesn't happen, electric field has to be at right angles. That means electric field all over the conductor are at right angles. There is no electric field along the conductor or on the surface of the conductor, along the conductor, or the potential at any point on the conductor will be a constant. Or we can say the surface of any charged conductor is an equipotential surface. The potential at any point on a charged conductor will be the same. So you don't have to go very far to look for an equipotential surface. Any conductor that carries a charge, the surface of that conductor is an equipotential surface. So since E equal to 0 on the surface, V remains a constant. Now look at this. If I take another surface there, this surface also is an equipotential surface. Why? Because all electric field lines are at right angles. Therefore, there is no electric field along that surface. The potential is a constant. That is also an equipotential surface. You can actually construct a large number of equipotential surfaces here, where the potential at any point will be the same. So, irrespective of the shape of a conductor doesn't have to be spherical for this. Irrespective of the shape of the conductor and the amount or the type of charge it carries, the surface of a charged conductor is always an equipotential surface. Isn't that beautiful? Equipotential surfaces can also be constructed outside a conductor by drawing a surface that is at right angles to the electric field. As long as you draw a surface that will be at right angles to the field always, that surface will be an equipotential surface. Let's now talk about distribution of electric charges on a conductor. Now, if you charge a conductor, will the charges be distributed uniformly all over the conductor? What do you think? What will be the distribution of electric charges on a charged conductor? Now, consider a conductor of shape like this. Now, if you charge a conductor like this, give some excess charge, how will the charges be distributed? Will the charges be distributed uniformly all over the surface? You can see all the principles we talked about are illustrated here. And everywhere on the surface of the conductor, the electric field is at right angles. Alright, let's consider two regions A and B. Now, this is part of a circle of large radius, is that right? Part of a circle of large radius, and this is part of a circle of small radius. Now, the radius of curvature of the surface is greater at A than B. So I hope you understand. At A, if you consider the curvature, the radius of curvature is small there. At B, and the radius of curvature is large at A. If R1 is the radius of curvature at A and R2 is the radius of curvature at B, then we say R1 is much greater than R2. Now, if sigma 1 is the surface charge density at A and sigma 2 the surface charge density at B, then approximate expressions for potentials at A and B can be written using the surface charge density. I can now write approximate expressions for potentials. Potential at A is sigma 1 r1. The surface charge density multiplied by the radius. Similarly, the potential at B is sigma 2 r2. Now, you know that the surface of any charged conductor is an equipotential surface. That means the potential at any point on the surface of the conductor must be the same. So potential at A equal to potential at B. Alright, since the surface of the conductor is an equipotential surface, potential at A equal to potential at B, therefore I can write sigma 1 R1 equal to sigma 2 R2. Since R2 is less than R1, is that right? R2, the radius of curvature here, is much less than the radius of curvature R1. That means, in order that this equation may be true, since R2 is smaller than R1, sigma 2 has to be greater than sigma 1. So sigma 2, therefore, is greater than sigma 1. What does that mean? It means the surface charge density at B will be much greater. Look at my diagram here. Charges are concentrated there, whereas at A, charges are farther separated. So the surface charge density sigma is much greater at B than at A. Now, what does that mean? The charge density is greater where the radius is smaller. Alright, this means that the surface charge density at sharp corners and pointed ends of the conductor will be much greater than at flat surfaces. So, if a surface is flat, the charges will be uniformly distributed. Whereas, if you have pointed ends, now look at this conductor. Now, where will the charge density be greater? You can see the radius is very small at A and very large at B. So, and very, very small at F. So the charge concentration or the surface charge density will be much greater at F than at E, much greater at A than at B, and so on. So charges tend to concentrate at pointed edges, and that is an important property which has useful applications. Now, actually this property, before I go to describe dielectric breakdown, let me show you some applications of that. Have you heard of lightning arresters or lightning conductor? A lightning arrestor is actually pointed metal rods like this, which are connected to the earth, grounded. Now, why are they useful in arresting lightning or thunder? Have you seen things like this on tall buildings, lightning conductors? Now what happens is, if there is a big cloud build-up, and inside the cloud, let's say there are lots of positive charges. Now, the presence of these positive charges on the cloud will make all negative charges to go down to the earth, and an accumulation of positive charges at the pointed ends. You understand that? The presence of these positive charge will actually induce a negative charge. Now, what I said is not correct. Because of the presence of the positive charge, negative charges from the earth will move and concentrate on these pointed ends. So what you have at the pointed ends will be concentration of negative charges. You see that? And because the ends are pointed, these charges will be very highly concentrated there. And this very high concentration of positive charges will gradually neutralize the positive charges in the cloud, thereby reducing the prospects of a dielectric breakdown. You remember I told you the prospect of a dielectric breakdown. If the charges accumulate and the potential increases, the dielectric breakdown occurs and lightning and thunder occurs. What happens is the lightning conductors will prevent that by gradually neutralizing all these charges on the cloud. A very useful application of this phenomenon. Now, we know what dielectric breakdown is. Air is normally an insulator. A good insulator is called a dielectric. We will see that in our next lesson also. A very high electric field produces ionization in air and other dielectrics and make them conducting. I told you about that a little while ago. This phenomenon is called dielectric breakdown. Now, dielectric breakdown happens in air when the electric field is greater than this, 3 times 10 to the 6th volts per meter. We talked about that. Now, here is a picture of lightning. Now, how does lightning occur? When there is a buildup of clouds and the electric field produced by the electric charges in the cloud is greater than this value, dielectric breakdown occurs. There is high level ionization in the air. Large amount of electric current flows from the cloud to the ground. And if you happen to be on its path, you know God only can help you. Alright. Now suppose a big, old, negatively charged up cloud passes overhead. Nearby conducting ground acquires an induced positive charge, establishing an electric field between the cloud and the earth. If the electric field exceeds that maximum value, dielectric breakdown occurs and a sudden burst of discharge occurs between the electric cloud and the earth, burning anything in its path. Houses, humans, animals, and so on. This devastating effects of lightning can be prevented by lightning arresters, and that's what I demonstrated to you. Now, here is a good illustration of how charges get built up in the cloud and they induce opposite charge on the ground, and how the electric discharge between them causes lightning and thunder. You see, when the charges get built up, the electric field increases, dielectric breakdown occurs. And that is the process of lightning and thunder. Well, let's close this lesson. Alright. Let's see if we can do this problem before closing. 2 horizontal metal plates are separated by 10 centimeter, and an electric field between them has a magnitude of 1 times 10 to the 4 Newton per coulomb, directed from the lower plate to the upper plate as shown like this. 2 metal plates separated so that there's an electric field like this. What is the charge density on the lower plate? Well, the electric field between the 2 plates is E equal to sigma over epsilon naught. I hope you remember that one. We discussed that earlier. If you got 2 metal plates, one positive, here this is positive, that is negative, each will produce a field of sigma over 2 epsilon naught. They will add up to give you sigma over epsilon naught. Therefore, sigma equal to E epsilon naught. We know E that is given to us, and this is epsilon naught. Therefore, sigma is 8.85 times 10 to the negative 8 coulombs per meter squared, and that is the charge density on the upper plate. The charge density, you see, the upper plate is negative. Therefore, the charge density must be negative on the upper plate. The direction of E suggests that the upper plate is negative and the lower plate is positive. Therefore, the charge density on the upper plate is negative. Second, what is the charge density on the lower plate? Well, the charge density on the upper plate is negative and the charge density on the lower plate is the same quantity but positive. Okay, third, what is the potential difference between the plates? If you know the equation we use for that, potential or the relation between E and V, do you remember? E equal to negative delta V over delta X. Therefore, delta V is negative E delta X. We know E, we know delta X. Delta X is the separation between the plates. Therefore, the potential difference between the plates is negative 1000 volts. Now, a small particle of mass m equal to 10 to the negative 5 kilogram and carrying a charge Q is in equilibrium there. The lower plate is grounded, means that the potential is zero. Well, what is the potential of the upper plate if the lower plate is grounded? If the lower plate is grounded, its potential is zero. Therefore, the potential of the upper plate is negative 1000 volts. Alright? And finally, when the particle is in equilibrium, if a particle is here, it is in equilibrium means it has a weight mg acting down and an electric force acting upward. How much is the electric force? It is Q divided by the electric field. That means when it is in equilibrium, these two are the same. QE equal to mg or Q equal to mg divided by E. That will be, we got all those values. That will be 9.8 times 10 to the negative 9 coulomb. Now, I rushed through this problem, but it's a very simple one. I want you to go through that one more time. I rushed through because the tape is finishing. Alright, this is now time for you to review the unit on electricity. Get ready for the next test. Alright, I'll see you for the next unit. Alright, another time.